So with random variables, we're still going to have some properties of probability. We're still going to be working with some of the probability topics that we were discussing in Chapter 5, but we're going to be talking about it a little bit differently here. So we're going to start today in Section 6.1. We're going to talk about a certain type of random variables. They're going to be discrete random variables. So there's two types we're going to discuss or mention today. We're going to really go into discrete random variables. We're going to talk about how to do expected value, how to do standard deviation. The other thing to brace yourselves for, tomorrow when we talk about continuous random variables require normal distribution calculations. That is Chapter 2 material. You need to be able to find z-scores, use z-scores to find probabilities, and so on. So that Chapter 2 material I told you would be coming back eventually, and here's where it's going to. So starting tomorrow, you're going to start seeing that table Z stuff again. That's part of what makes this particular chapter a little bit tougher. So just be aware of that. All right, first thing, we need to define random variables. What are they? So a random variable assumes a value based on the outcome of a random event. So it's a variable that assumes a value based on the outcome of a random event. So that might be, we flip a coin 5 times, and we want to know the number of heads that occur. The number of heads would be a random variable. It takes on any number of values from 0 to 5 based on the random outcome of flipping a coin. So it's not really that much different than anything we've been discussing previously. It's a random phenomenon, but it's the values that this particular variable can take on involving that particular random phenomenon. Flipping a coin, rolling dice, drawing a card, things like that. So when we denote random variables, we define them with a capital letter. Most often, they like to use X and Y and Z. Those are the three they tend to use most often because those are the ones you guys are used to using as far as variables are concerned. But you can label your random variable with any capital letter. If it's easier to keep track of by calling it A, then you can call it A. It just needs to be a capital letter to denote what the variable is. When you name it then, the value that the variable can take on, so the different values that can occur, will be denoted with the corresponding lowercase letter. And that is a distinction that needs to be made, because I will count off for that if you say capital X equals 2. Capital X is what the variable is. Lowercase x is the actual value it can take on. Or if you denoted your random variable as capital C, then lowercase c would be the value it can take. So capital letter is what you define the random variable as. Lowercase letter is a specific value of that particular random variable.
So would capital letter usually be like words like X?
Yes. So like in this case, if I was looking at, for my example, flipping a coin 5 times, capital X would equal the number of heads in 5 tosses. Okay? And then lowercase x could be 0, could be 1, 2, 3, 4, or 5. So yes, when you define your random variable with a capital letter, most often it's going to be a word description of what you're dealing with. And then the lowercase letter will be the actual numbers. Okay? So there are 2 types of random variables. The first type is called a discrete random variable. This goes along the lines of when we talked about discrete sample spaces and continuous sample spaces. Discrete means a variable that can take on one of a countable number of distinct outcomes. So within a range of values, there are only a certain number of values that are acceptable. For example, number of free throws made. So let's say someone takes 10 free throw shots. What's the number of shots that they make? Those can only be 0, 1, 2, 3, and so on. They're a listable set of values. Okay? So if you can take the different values for your variable and list it, that is a discrete random variable. The second type is called a continuous random variable. Continuous random variable goes along the same lines as continuous sample space. This was where we have a boundary of values, but we can have anything within those boundaries. So we wouldn't be able to list out every possible value that our variable can take on, because any infinite number of values would work. So a continuous random variable takes on any numeric value within a given range of values. So the number of hours a student studies for a test. So if we said they had anywhere from 2 to 4 hours of free time, the number of hours they spent studying in those 2 to 4 hours could be anything within those 2 to 4 hours. In a discrete case, we would be able to list all of the different values. In a continuous case, there's no way to list every possibility, because in that 2 to 4 hours, you could have studied any number of hours, any number of, or any fraction of hours, or whatever. So that's a continuous case. That's where we have an infinite number of values within our range. So, like we just said or discussed, discrete random variables, this is what we're going to discuss today. Continuous, we're going to discuss tomorrow. Now, with discrete random variables, the first thing we're going to talk about is called expected value. Now, expected value is going to come from the idea of a probability distribution. This is something we talked about last chapter. So a probability distribution for a random variable consists of the possible values for that random variable. So you need to list out every possible outcome for your particular variable, which is why this only works for discrete cases, because you have to list. So you list every possible outcome, and you need to give the probabilities that each of those values occurs. So you need to figure out what values your variable can take on and determine what the probability of each of those individual values is. So for instance, if we consider tossing a fair coin 3 times, we're going to define a random variable x as the number of heads we obtain. So when we flip it 3 times, we're looking at how many heads are going to happen in those 3 tosses. So if we think about that and we want to create our probability distribution, the first thing we need to figure out is, well, what values can my variable take on? So capital X, the number of heads obtained. That's what we're defining the variable to be. So our lowercase x values could be what? 0 through 3, so 0, 1, 2, or 3. Okay, we could get 0 heads, 1 head, 2 heads, 3 heads. Everyone okay with that? So, when we do that, we can list those out. Now, this second part with the tails, 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 heads, tails, tails, and stuff, that's not something you would need in your probability distribution. That's just going to be here for visualization here in a second when we talk probabilities. But what you would need to do is make a chart that tells what the lowercase x values can be. In this case, 0, 1, 2, or 3. That's the first part of your probability distribution. What are the values that can happen? The second part of your probability distribution involves the probability of each of those values. And here's where listing all these outcomes comes into play. So if I look, tossing a coin 3 times, there are 8 different outcomes. Okay? So there's only one outcome in which x is 0. There's only one time or one way we can actually get 0 heads. There are 3 different ways to get 1 head. It can be the first, second, or third flip. There's 3 ways to get 2 heads. That means we get 1 tail, so the tail can be the last, middle, or first. And then there's only 1 way to get all heads, and that's heads, heads, heads. So if I was going to calculate the corresponding probabilities, what is the probability that x equals 0? 1/8. What's the probability that x equals 1? 3/8. Probability that x equals 2? 3/8. And then the probability that x equals 3? 1/8. So here is what your probability distribution should look like. It's basically just a table of values. So the top row, you just define as your values for your random variables. So your lowercase x can be 0, 1, 2, or 3. And then you also need to give the corresponding probability. So the probability of getting 0 heads is 1 out of 8. Probability of getting 1 would be 3 out of 8, and so on. So when you're working with expected value, which we'll talk about here in a second, the first thing you need to discuss is your probability distribution. What are your different values, and what are their corresponding probabilities? This needs to happen every time. Okay? Now, with these probability distributions, we're still going to be interested sometimes in basic probabilities. So if I were to ask you, what does the probability that x is less than or equal to 2 mean in words? Here was something that you guys really struggled with on the last quiz. And this was why I said in the homework, you need to write your notation. You guys had no idea what the notation meant. You would get the words, and you would try to write notation, and the notation was nowhere close to what it needed to be. Or you'd see notation and have no idea what it meant. And we need to understand what those notations mean. So when I say, what's the probability that capital X is less than or equal to 2, what does that actually mean in words?
What's the probability of getting 2 or less heads?
All right, what's the probability that the number of heads we obtain is less than or equal to 2? So what's the probability that we get 2 heads or fewer in our scenario? Okay, so one of the things you guys really need to start doing is focusing on notation and what it means. You need to be able to translate between English and math. Okay, so in words, again, what's the probability that the number of heads we toss is less than or equal to 2? So if I wanted you to actually calculate that probability, what would we need to do? Add what up?
The probability of 0, 1, 2, 3.
The probability of getting 2 plus the probability of getting 1 plus the probability of getting 0, right? So this is an addition problem. So we would take our 3/8 plus 3/8 plus 1/8. So what would the probability that x is less than or equal to 2 be? Would be 7/8. Okay? So as far as your probability distribution goes, once you have it laid out, most of your probabilities should be pretty straightforward. It's just a matter of finding the ones you want and putting them all together. Okay? What if I want the probability that x is less than 2? How does that change, or does it change?
0.
All right, this time we're not interested in including 2 heads. We're saying we have to be strictly less than 2, which means we can only have 0 or 1 heads in this case, right? So we would take the probability of 1 plus the probability of 0. We get a total probability of 1/2. Okay? So be aware that when you get these types of questions, you have to pay close attention to whether it's less than or greater than, or whether it's less than or equal to, or greater than or equal to, because that will change what you include in your overall calculations. Everyone okay with that idea?
Do you also, for the number of heads, could you also use the complement rule, and the chances that it's like not?
Yes, you could. If we go back to this one, okay? So if we look at our probability distribution, the probability that x is less than or equal to 2, well, that's three different problems, right? Or three different parts we have to put together. So what we could look at is, well, if I want everything less than or equal to 2, that means I don't want 3, right? That's the only one I don't want. So if I take my 1 out of 8 chance of getting a 3 and subtract from 1, I still get my 7/8. So sometimes it might be easier to use that complement rule to shorten down your calculation. So yes, you could do that. Okay? Complement rule is always valid as long as you get the correct scenario going with it. Okay? All right. Any questions on the probability distribution and how to calculate probabilities with it? Okay? So then the next thing, this is going to be like the main part that we want to discuss today, because we've already discussed probabilities in the last chapter. Expected value. When we look at a random variable, what we want to know in most cases is what we can expect to happen if we were to create a random phenomenon over and over and over again. What's going to happen in the long run, or what can we expect to see? Okay? So, we expect a random variable to take on a certain value. If I were to flip a coin 3 times, over and over and over again, how many heads should I expect to obtain? Okay? So we're saying if I was doing it over and over again, sometimes I might get 0 heads, sometimes I might get 2 heads, sometimes I might get 3, sometimes I might get 1. What we want to know is if I were to do it constantly, how many heads could I expect to get every time I toss 3 times? Does that kind of make sense? So we're looking at the center of a distribution. That's why we use expected value, which is denoted with a capital E of x, or whatever you decide to call your variable. So if you used y for your variable, it'd be E of y. If you used a, E of a. So expected value you're going to see used either with a capital E, or you're going to see it denoted with a mu. Okay? And a lot of times, especially in the book, they might even go so far as to say mu of x or mu of y, so to differentiate between different random variables. So you need to understand that both of these notations, mu and E of x, mean the same thing. They're both expected values. Okay? So, what we're looking at here is basically trying to find, if we look at our probability distribution, and we look at this as an actual distribution, so we create a histogram. So we can create a histogram based on our probabilities. Getting a 0 had a 1 in 8 chance. Getting a 1, 3 in 8. 2, 3 in 8. 3, 1 in 8. So if we list it out in histogram form, where would the mean of our distribution lie? Between 1 and 2. Anywhere between 1 and 2, or specifically somewhere between 1 and 2? Should be directly in the middle, right? So right at 1.5 is what we would expect. So what we're looking at here is we're looking for the center of our distribution. Now, if we had to graph every single time and try to find a center, that would take a lot of time. So we're going to discuss a shorter method using a formula to calculate this expected value. But we can see from this distribution that if we were to flip 3 coins over and over and over again, on average, we should expect to see how many heads? 1.5. Now, when you do these, again, these are expected values. These are theoretical. So sometimes it may not exactly make sense in the nature of the problem. Because if I were to flip 3 coins, could I ever actually get 1.5 heads as one of my options? No. So this is an average, which is what you need to keep in mind. It's an average value in the long run, if you were to do the same process over and over again. Everyone okay so far? Okay. So let's talk about how to actually calculate expected value, because we don't want to have to sit there and make histograms every single time and then try to discover where that center is going to be. So the expected value of a discrete random variable is the average of the possible outcomes with the weighted, or with each outcome weighted by its probability. So basically, what's the average of the outcome times its probability? So we're calculating our average by taking our values times the probabilities of those values. So in notation, this is what we're looking at. So notice I went ahead and used both notations here. Mu, E of x, they both mean the same thing. We're both talking expected values. So what you're going to do, sigma means sum. So we're going to add up a bunch of values. Those values are going to be calculated by taking the value of my variable, that's my lowercase x, times the probability of that corresponding x value. So think about that in terms of our coin toss. Okay, so here was our probability distribution, yes? So x could be 0, 1, 2, or 3. The probability that x was 0 was 1/8. The probability that x was 1 was 3/8, and so on. So if I wanted to use my formula here to calculate the expected value, I'm going to take each specific value of x times its probability and add them all together. So I start with my first value. So I'm going to take 0 times 1/8 plus my next value, which is 1 times 3/8 plus my next value, which is 2 times its probability, 3/8 plus my last value, 3 times its probability of 1/8. So when you're calculating expected value, you need your probability distribution, and then it's just a matter of taking each value times its probability and then adding them all together. So if we were to take these and plug them in, so you can either use your calculator or just work it out in your head. So 0 times 1/8 is going to go to 0, plus 1 times 3/8 is going to be 3/8, 2 times 3/8 is going to be 6/8, 3 times 1/8 is going to be 3/8. So if we take our 3/8 plus 6/8 plus 3/8, we get 12/8. And 12 over 8 would reduce down to 3 over 2, which would be 1.5. So whether we use the histogram and find the center that way, or we use this easier formula, we still get that we should expect to see 1.5 heads every time we flip 3 coins. Okay with that idea? Okay. Now, when you go to create your expected value, one of the things you want to do before you start your calculation, because there are times where you might be doing there might be a lot of different values for your variable. So before you go ahead and do a whole lot of work here, make sure every time that every possible outcome is accounted for, and verify that you have a valid probability model to start with. So make sure your sample space adds up to 1. Make sure every probability adds up to 1. Make sure every probability is between 0 and 1. So make sure everything looks good first before you start doing all this extra work of calculating expected value. Because if you're missing anything, you're going to be getting incorrect values. Okay? So always double check your probability distribution. Now, with expected value, since we're calculating a mean, anytime we calculate a measure of center, a mean, we also need a measure of spread. Mean always went with standard deviation. So now we're going to talk about standard deviation. So we know, in essence, that when I flip my coin 3 times, I should expect to see 1.5 heads. But first of all, we know that 1.5 heads is not a possibility if I do it 1 time. Also, I know that my different values are going to vary every time I do it. So we need to know how much spread is around that center value. How much can we expect our values to deviate from that expected value? That's where standard deviation is going to come into play. So we're going to calculate standard deviation for random variables almost the exact same way we did it for regular data. However, this formula we use here is going to be a little bit simpler than the standard deviation formula we had before. Okay? So, along the same lines of expected value, we're going to use that same notation to calculate. Now, first thing we're going to calculate is what we call variance. If you remember way back in chapter 1 when we were talking about standard deviation, variance is standard deviation squared. So a couple of things to take note of here. The notation, this lowercase sigma on its own is standard deviation. Lowercase sigma squared is variance. So when you see this lowercase sigma squared, we're talking variance. The other way to denote variance are the letters VAR with whatever random variable you're discussing. So in this case, the variance of x. So these two notations are ones you need to understand and recognize. When you see them, you know they're talking variance. That is standard deviation squared. Now, in order to calculate standard deviation, we have to solve this first. So we always need to calculate variance first, and then once we have variance, we can calculate standard deviation. So the formula here is very similar to how we calculated expected value. Expected value was x times probability of x. The only difference now is that we have to calculate our deviations from the mean. So we take our value minus mean squared and multiply that by the probability. And then we continue that process. So if we think about our coin toss example, okay, so if we go back to this probability distribution here, our mean was 1.5, yes? So if I wanted the variance for this particular distribution, so if I wanted to calculate my variance, I would start with my first value, 0, minus the mean, so minus 1.5, squared, times the probability of 0, which was 1/8. Plus, I go to my next value, which was 1, minus the mean, squared, times the probability of 3/8, and so on. Now this equation, once you get it all written out, the easiest thing to do is in your calculator, do it all at once and type it in exactly as you see it. So all the parentheses in the same spot, square it and everything in the right spot there. If you plug it all in at once, then it's going to give you the exact value when you get to the end. So you're just going to continue this process until you've accounted for all of your variables. Okay, so once we did 1 through 0 and 1, all you have to do then is do 2 and 3, and then put it all together. Everyone okay with that idea? So basically here, as far as variance goes, it's a matter of memorizing and being able to apply a formula. Okay? So the value minus the mean squared times the probability of that value. And then you add them all up at the end. Okay? Now, once I have my variance, so once I've actually gone through this process and I calculate variance, what am I going to have to do to find standard deviation? Take the square root of it. So we calculate variance using the given formula, and then once we have that, we can take the square root, which gives us our lowercase sigma alone, which gives us standard deviation. And in this case, standard deviation can also be denoted as a capital SD of whatever variable we're looking at, so in this case x. So all we need to do here is take the square root of the variance. So on each of these problems, you got to pay attention to what they're asking for. Sometimes they're going to ask for expected value and that's it. Other times they might ask for standard deviation, and if you need standard deviation, you have to calculate variance first, then take that value and square root it to find your standard deviation. One of the things that you must have in your homework for these problems is correct notation. You need to be using mu or e of x or e of y or whatever you call your variable when you're talking expected value. You have to have sigma squared or var x if you're talking variance, or you need sigma and s dx if you're talking standard deviation. I will not accept homework, I will not give you credit if all I see are numbers. If you don't tell me what that number actually relates to, you are not getting credit. Okay? So you have to have the notation for what you actually calculate. Everyone understand that? All right. So let's just look at a couple more examples here. You don't necessarily have to write these down. You can just kind of follow along. It's the same process we just got done discussing, just with a different example. So a baby's APGAR score is the sum of the ratings on each of 5 scales, which gives a whole number value from 0 to 10. So we're going to let our random variable x equal an APGAR score for a randomly selected newborn. So we know that they have a value from 0 to 10. Okay? Now what they've done is they've compiled probabilities based on countless numbers of observations with babies and their APGAR scores. So they just collected a bunch of data on babies and what their APGAR scores are and created these probabilities empirically. So based on lots and lots of data being observed over and over again. Okay? So for instance here, the probability that a baby gets an APGAR score of 8 would be 31.9%. Okay? So we have our values, 0 through 10, and then the probability for each of those values listed below. So once I know my probability distribution, first thing I want to do is calculate the mean. So mean and expected value are the same thing. When they say calculate the mean, they're telling you to calculate expected value, or vice versa. So those two words mean the same thing in these contexts. So calculate the mean of the random variable x and interpret the value in context. So if I wanted to calculate my expected value, what would I need to do here? Yeah, basically just go through my process of averaging out all of my values with their probabilities. So I would take 0 times 0.001 plus 1 times 0.006 plus 2 times 0.007, and so on. Okay, so I would just go through this process of multiplying every value by its probability and adding them all together. So we get an expected value of 8.128. So with this value of 8.128, the next thing it said to do was interpret. So what does this mean? Okay, so average value of what? We need context. Okay, you're on the right track.
If you randomly select a baby, they're most likely going to get an 8.1 for their score.
Okay, so the mean APGAR score for a randomly selected newborn is 8.128. So what we're saying is, if we were to select a baby at random, we should expect their APGAR score to be about 8.128. Okay? Now, obviously, we know that they can't get an 8.128. Again, this is an average, so it's going to have decimals when maybe decimals aren't applicable. And again, because it's theoretical. Okay? We know that any chosen baby is not ever going to be exactly. Not all of them come out to be 8. Okay? Some come out to be lower or higher. Just depends on the baby.
So then, when we're explaining it in words, do we keep it with the decimal even if it's not applicable?
Yes. Yep, the expected value you leave exactly as it is. So if it's decimal, you leave it with decimal. If it's exact, you leave it as exact. Yes. Because the expected value is just that. It's an expected value, not a specific value from the set of values you have. Okay? So it's just that average value based on what we see. So when you interpret expected value, this first statement is what you need to have. Okay, with context involved. So in this case, the mean APGAR score of a randomly selected newborn is 8.128. Now, if we take the same information and we want to calculate standard deviation. So if I want to do standard deviation, what do I need to calculate first? Variance. So we need to calculate our variance. Now, variance in this case would take a little bit of time. Okay, so on a problem like this where we have 10 different values to account for, it will take a little bit of time, but the process is the same all the way throughout. Value minus mean, so 0 minus 8.128, square that, times the probability. Plus 1 minus 8.128, square that result, times 0.006, and then we continue on throughout the entire process. Okay? So in this case, we get a variance of 2.066. So if I know what my variance is, how do I get my standard deviation? Take the square root. Okay? So the square root would be 1.437. Now, interpreting standard deviation is exactly the same as when we interpreted standard deviation before. And again, some of you probably need some practice with that. So when you interpret standard deviation, a randomly selected baby's APGAR score will typically differ from the mean by about 1.4 units. So when you're interpreting standard deviation, it is the typical distance from the mean score. Okay, that is the wording I need to see in your explanation. The typical difference from the mean score. The only other thing you have to add with that then is context. What are you actually measuring in the problem? Okay with all that? All right. So there's your assignment.